Welcome back to our third and final segment. We're still looking at percentage yield. Now we'll focus our attention on a different example altogether and see how exactly we know what's the approach in terms of solving problems that involve percentage yield. Right. So we're still talking balanced equations, but our focus is on the yield in this case. That's as far as stoichiometric calculations are concerned, right? So here we've got a scenario that says methanol, CH3OH, that's the molecular formula, that's the name of the substance, can be burnt in oxygen, okay, to provide energy, or it can be decomposed to form hydrogen gas according to the following equation. As to whether the equation is balanced or not, it's something that remains to be seen. However, take note that this is a decomposition type of a reaction, okay? So according to the equation, if you look at it in terms of carbon, okay, there's one carbon on the left and one on the right. Okay, oxygen is fine. If you look at hydrogen, there's 4 on the reactants, and then there's 2 on the product. It means in terms of balancing, then this will be 2. So the stoichiometric ratio in which they react is 1 methanol is to 2 hydrogen is to 1 carbon monoxide. Now we are told that that mass, which is 125 grams of methanol, is decomposed. We are interested in determining the theoretical yield of hydrogen gas, right? So our focus will be on methanol to hydrogen. So in terms of stoichiometric ratio, we'll look at those 2 to be precise, right? Okay, so the balanced equation, we said here there's 2 moles. So the stoichiometric ratio in which they react is 1 is to 2, right? So we are told that there is a sample of 125 grams of methanol, okay? Now, what is the theoretical yield of hydrogen? Now, the theoretical yield is what we expect in terms of the stoichiometric ratio in that these substances react to form the other. So as a result, we'll look at, let's change this mass of 125 grams into moles. Why the moles? Okay, the question that is very important to us is that, okay, remember, the mole is, the SI unit of quantity of matter. So when we talk amount of substance in a chemical change or in a chemical reaction or in stoichiometry, so the mole is our point of reference. Now, we ask ourselves, in a 125 gram sample of methanol, how many moles of it are present? So number of moles of methanol, which is CH3OH, right, is equals to the mass of the sample divided by the molar mass, okay? Now, the sample mass is given as 125 grams, right? 125 grams. The molar mass of methanol is 32 grams per mole. Where did we get the 32? Carbon is 12 plus hydrogen, which is 4, which is 16 plus another 16 for oxygen. That gives us 32, okay, grams per mole, all right? So whatever we're going to get here in terms of the number of moles of methanol, CH3OH, okay, is equals to that. So if we go to our calculator, you'd immediately realize that, okay, so in this case, what do we have? We've got 125 grams divided by 32 grams per mole. This gives us that as a decimal fraction is 3,91. Okay, so how many moles of methanol are present in 125 gram sample? It's 3,91 moles, okay? So this gives us 3,91 moles, right? Now, if 125 is the mass of the sample, now every mole of methanol gives us double the number of moles of hydrogen. So in other words, number of moles of hydrogen based on the stoichiometric ratio is 1 is to 2. So it's going to be 2 times the number of moles of methanol. So it's 2 multiplied by 3,91, right? So the number of moles of hydrogen gas, okay, according to the stoichiometric ratio is equals to, if we go back to our calculator, so that's 3,91 multiplied by 2. What do we get? It gives us 7,81. So it's 7,81 moles, all right? 7,81 moles, okay? So that's the number of moles. But the question asked us to determine the theoretical yield. It should be actually the mass, okay, in grams. So we need to change those moles back to the mass. So we know that number of moles of hydrogen gas is actually equals to mass of hydrogen over the molar mass of hydrogen. Okay, so now we have the number of moles of hydrogen that will be formed from 125 gram sample. So this will be 7,81 is equals to the mass over the molar mass of hydrogen, which is 2, okay? The molar mass comes from that formula. Take note, we do not multiply by the coefficient in this case, which is the stoichiometric ratio, because the coefficients, they simply give us the stoichiometric ratio in which they react. So the mass is equals to 2 multiplied by 7,81, right? So if we go back, this 7,81 multiplied by 2, okay, this gives us the actual mass of hydrogen. So the theoretical yield of is that the actual mass of hydrogen that will be formed is equals to 15,6 grams, 625, okay? So it's 1615,625, okay, grams. This is what will be formed in terms of hydrogen gas. So we can say the mass of hydrogen gas that will be formed is exactly that. But then the question that follows up, it says we must be able to determine the percentage yield. Now we want to express the actual yield. This is the actual yield because it says only 13,6 grams were formed, okay, of hydrogen gas. But what did we expect? The expected amount was 15,625, okay? So if that's the case, we would say, okay, this is a percentage yield, okay, is equals to the actual yield, which is 13,6, okay, divided by the expected one, which is the theoretical. In this case, the theoretical is 15,625, okay? So that's 15,625 multiplied by 100. That will give us the percentage yield. So our percentage yield in this case would be, okay, 13,6, right? 13,6, which is the actual yield divided by 15,625, okay? Equals to multiply that by 100. It will give us the percentage. So our percentage is 87,04, okay? So this is 87,04%. So always leave your answer in 2 decimal places, right? Okay, now we've got another typical example, right, which says in the reaction below, this is the one for formation of ammonia, which somehow looks very familiar to us, okay? In the first segment, we managed to do the balancing act using the simulation. So we're told that there's 30 grams of nitrogen which react completely to form that amount of ammonia. So this 26,6 is the actual yield, okay? This is the actual yield, okay? That's what was obtained in practice, and then it was obtained from 30 grams of nitrogen. So we want to calculate the percentage yield of ammonia in this case, right? So we would ask ourselves, is the equation balanced, yes or no? It's definitely not balanced because we remember from the balanced equation, it's 1 mole of nitrogen is to 3 moles of hydrogen is to 2 moles of ammonia. So we need a 3 there and we need a 2 there. Okay, so that's the stoichiometric ratio in which they react with each other. So the question that follows is, for us to get the percentage yield, we need to find the expected yield first, which is the theoretical, to say if there is 30 grams of nitrogen that react completely, of these 30 grams, how much do we get in terms of ammonia? So the first question, the first part of our problem solving has to do with how many moles of nitrogen are present in the 30 gram sample of nitrogen gas. So number of moles of nitrogen gas, okay, is equals to mass of sample divided by the molar mass, okay? So the mass of this sample is 30 grams, okay? So we've got 30 grams, okay, divided by the molar mass of nitrogen gas. Each nitrogen atom has a mass of 14 grams per mole. If so, it's a diatomic molecule. This gives us 28 grams per mole, okay, from the periodic table of elements. So how many moles of nitrogen are present in that? So we can quickly determine that. Right, so what do we have? We've got 30 divided by 28. Okay, this is the actual number of moles, so which is 1,07. Okay, 1,07 moles. All right. Okay, so that's the number of moles of nitrogen. But then, how many moles of ammonia must be formed? Okay, every mole of nitrogen forms double the number of moles of ammonia. So from the stoichiometric ratio, we know that number of moles of ammonia in this case, okay, will be equals to 2 multiplied by the number of moles of nitrogen, which is 1,07, right? So this gives us, if we double that, what do we get? Okay, we'll multiply that by 2, we'll get, okay, 2,14 moles, okay, 2,14, right? So this is 2,14 moles. Now the next question is, in 2,14 moles, what's the actual mass? Let's change these moles into the mass so that we get the actual yield, the theoretical yield. So what do we have? We know that number of moles of ammonia, right? Number of moles of ammonia is equals to mass, okay, divided by the molar mass. So we've got the moles in this case, which is 2,14. So 2,14 is equals to whatever mass we'll get. The molar mass of ammonia is what we need. It's 17 grams per mole, okay? 17. So the mass that is we're going to get is 17 multiplied by 2,14, right? Okay. So we'll multiply this by 17 to get the mass of ammonia, which is 36,42, okay? So this is 36, right? Okay, if we go back, this is 36,12. Okay, let's just go back to that so that we get that. So the calculator gave us a value of, just to verify that, 36,43, okay? So the mass is 36,43, okay, for 3 grams. All right, so if we want to get the percentage yield, because that's the question that it asked us, okay? We want to get the percentage yield. Let's use those values then. So the percentage yield of ammonia, okay, is actually equals to, you know, the actual yield. So if we look at the actual yield is 26,6 grams. That's what was formed, okay? So it's 26,6 grams, okay? This is the actual. What did we expect? That's our theoretical yield. Our theoretical yield in this case is 36,43, right? So that's 36,43. We multiply this by 100. It will give us the percentage yield of ammonia, okay? So if we can quickly verify that from the calculator. So we have the calculation in terms of 26,6, okay, divided by the theoretical yield, what we expected, okay, the one that we calculated from the stoichiometric ratio. So this is the actual yield, okay, just to go back. So this is the actual yield, okay. This 26,6 is the actual, okay, yield. This is what was obtained, okay. And then this is actually our theoretical, the one that we determined from the stoichiometric ratio. So this is our theoretical yield, right? Just to put things into perspective. Then this gives us, if we go to our calculator just to verify that. So it's 26,6 divided by 36,43, right? Okay, we multiply that by 100 so that we get that percentage. So the value as a decimal fraction is 73,02%, okay? So it's 73,02%. So that's the percentage yield of ammonia, right? Okay, so in closing, what are we saying? The mole is the SI unit of quantity of matter, Okay, just to drive that point, you'd realize every time we were given the mass of sample of a substance, we had to carry out calculations to express it in terms of the mole, because the mole is the SI unit, and we can compare moles and moles, so that's why we had to convert the mass of each sample into the moles. Okay, and then the balanced equation gives us the mole ratio. We want to emphasize on that, in which these substances react with each other. And in any chemical reaction, the total mass remains constant. So this is the law of conservation of mass, right? Okay, and then also when it comes to the theoretical yield, we understand that this is the maximum amount of product that is expected as calculated from the balanced equation of reaction, which is why we always balance the reaction. And then the actual yield is used to determine the large-scale production of chemicals and to check whether the production process is actually viable. So a higher percentage is an indication that, yes, indeed, the production process is economically viable. Okay, so that's how we calculated our percentage yield of a substance, right? So having said that, I think we managed to put these two pieces together in terms of how then do we use the stoichiometric ratio to determine or to predict, the amount of substance using the mole, which is the SI unit. So that those are some of the very, very important, aspects of our discussion today. So in a nutshell, the mole is used to determine, any quantitative aspect of any reaction. Why? Because the mole is the SI unit. And then we can do all these calculations, but we must base our understanding on the importance of how a chemical reaction takes place in terms of quantities. Having said that, this brings us to the end of our session. Cheers and bye-bye for now.